This is a software tool developed for scheduling track geometry maintenance. It allows you to manage the entire process, from loading the raw data, pre-processing and aligning it, detecting unregistered tampings and shocks, to modeling degradation rates and optimizing both corrective and preventive maintenance strategies. To begin, you can upload your raw data into the system. The software will analyze the uploaded files and add them to its database if the data is new and valid. If only part of the dataset is suitable, the system will add only that portion. Once your data is uploaded, you can visualize it by selecting the desired channel, corridor, markers, and inspection dates. You can choose as many inspection records as you want. It's also possible to view heat maps displaying characteristics such as standard deviation, kurtosis, or other statistical measures for each segment across different inspection dates. In addition to these, the software can also highlight isolated defects in the track geometry data. Due to the significant misalignment in raw data, proper alignment is of utmost importance. This section allows you to pre-process and align your data effectively. 3 different approaches have been developed for alignment. First, you can select a specific marker range and align it using a reference inspection date. This method sends all available inspection data within that range for alignment. Alternatively, you may align only selected markers. As shown here, the raw data initially suffers from substantial positional error. After selecting your desired inspection dates and sending them for alignment, you can choose from multiple alignment methods. These alignment methods were developed as part of my research in collaboration with my co-authors. You can explore them further in our 3 peer-reviewed journal papers, where we present each method along with its advantages and limitations. Once aligned, your data will be accurately positioned. Another approach, called marker-based, lets you choose a channel of interest. This approach automatically selects the most appropriate reference inspection based on data quality. It's a recommended approach, especially effective for using in other sections while detecting unregistered tampings and shocks, modeling isolated defects, and scheduling maintenance. At any point, you can visualize your aligned data. You can also generate a heat map showing measurements collected every 25 centimeters to observe trends over time. In addition, track geometry degradation can be monitored using segment-wise standard deviation or kurtosis. Similarly, isolated defect trends can be tracked across multiple inspections. You can upload known tamping or maintenance dates for each segment into the software. This information is essential when modeling degradation and scheduling future maintenance. However, the software can automatically detect tamping events or shocks that occurred but were not previously registered. After identification, these detected events can be reviewed and, if deemed accurate, used to replace all existing maintenance records. Or you may select to add only one tamping date or a new list of tampings. With precise alignment and accurate tamping event detection, you can model degradation more effectively. This includes modeling based on aggregated quality indices such as standard deviation, as well as more detailed micro and macro-level degradation of isolated defects. For a deeper understanding, refer to my research on the assessment of railway track preventive and corrective tamping recovery. Once the data is prepared, you can proceed to generate an optimized maintenance schedule. Select your target track segments. Configure initial maintenance parameters. Define the genetic algorithm settings. Choose your modeling preferences and track speed classes. Then run the optimization. The system will compute the optimal schedule. Here you can see the resulting maintenance windows and the segments selected for tamping. As it's shown here, the standard deviation values of all segments remain below 1.5, which is the defined intervention threshold. Additionally, the heat map confirms that isolated defect values also remain under the planning limit. A detailed schedule table is provided, showing when each segment is expected to undergo preventive or corrective maintenance. This optimization is based on a model developed through collaborative research with my co-authors and published in our reference paper. For a deeper understanding of the model and its advantages, please explore the publication. Finally, you can visualize the current status of the track geometry on a map. Red colors highlight critical segments based on predefined thresholds. In this example, data from only 11 segments, covering approximately 2 kilometers, is shown. To analyze additional sections of track, simply upload more data into the system.